Circle is a C word. That's right. This is Geometry Chapter 12, Lesson 1. I'm on page 484. Circles, radii, and chords. Okay, you have to know the definition of a circle. A circle is a set of all points that lie on a plane that are equidistant from the center. That's what that definition means. It's a set of all points in a plane that are a given distance from a given point on the plane. So here's the center. What is the distance of every point on the circle from the center? We call it the radius. That is correct. So literally when a calculator or a computer program is graphing something, they do it in dots. You would think it looks like a line. It literally does look like a line, but it is literally dots. So literally it is every point. This is what it does, okay? But you know, it ends up looking like this. Well, it looks a little better than that. Such that that's a radius. That's a radius. They do not look equal. That's a radius. That's a radius. And what do we know about the radii in a, do not laugh at my circle. Actually, you can. Laugh with me. Laugh with me.
We had Mr. Folk's flashing for science class.
Okay, so what do we know about every radius inside one circle? What do we know, Luke? That is correct. All radii in a circle, in a particular circle, they are all equal. All radii in a particular circle are equal. All right, so what is a radius? A radius, what are the endpoints of a radii, of a radius? A point on the circle and the center, right? That's a radius. It goes from the center to any point on the circle. It's actually a line segment. We talked about concentric circles. What is true about concentric circles? That's another word. It's like the picture on the previous page. Selby?
Their center is the same.
That's right. They all share the same center. It's like when we drew the circles that had a radius of 2, that had a radius of 4, that had a radius of 7. They all had the same center. Those are called concentric circles. All right, so we've learned the definition of a circle. It's all points equidistant on a plane from the center of the circle. That's the point they're talking about. We've learned what a radius is. You knew what a radii was, right? We know what concentric circles are. Now we're going to talk about a chord. I'll write it, chord.
Oh, we learned it. Oh, wait,
Chords. What is a chord? A chord. Like, not all in one, a chord, but is a singular chord. Yes?
A chord is a line segment that connects 2 points of the circle.
Correct.
Does a radius count? I mean, a diameter count as a chord?
The diameter is the longest chord in any circle.
Oh.
So a chord is a segment inside a circle whose endpoints actually lie on the circle. A radius is not a chord. A radius is a radius. Its endpoints are not both on the circle. The diameter is the longest chord in any circle. Look, here's a chord. This is a chord. There are certain things that are true about chords. One that is not in your book and one that is in your book. So if I have a diameter, all right, if I have a diameter, I know it's a diameter because it goes through the center of a circle. And and it intersects a chord. Mine's not gonna be very pretty. I need to redraw this so that it looks the way it's supposed to look. Let me do this. This will be my diameter. Okay, that looks a little better. All right, so we're talking about this chord. We'll call it a chord. I was gonna call it C1. All right, there is something that we can know about this chord that intersects the chord. Yep.
Is it perpendicular?
Right. If we know it's perpendicular, then we know it bisects. So if we know it's perpendicular, then it bisects the chord. If a line through the center of a circle is perpendicular to the chord, it also bisects it. The reverse is also true. The inverse, not the reverse. If I know it bisects the chord, then what can I know? It's perpendicular. That's correct. So if I know that that diameter is perpendicular to the chord, then I can know that it bisects it. By the same token, if I know that the diameter bisects that chord, then I can say it is perpendicular to it. Okay, let me tell you how this usually looks on the ACT. You see the center? You see the chord? That's a radius, isn't it? Typically, the radius isn't drawn, but they will give you this length, and they'll give you the entire length of this chord, which we're going to say 8, and they don't have the radius drawn. But they're going to ask you, what's the length of the radius? So you're always going to draw a right triangle from the center to the end of that. What do we know about this length? It divides it in half. So this has to be 4. So what must the radius be? 5. It's a 3, 4, 5. All right, so now let's do a different one. I'm gonna do, I don't know, we'll do it this way. Here's the diameter. We'll do a chord. We'll call that chord 1, then they don't label chords. But we'll say this length is, this whole length is 16, and this length is 6. What's the length of a radius? They would put a perpendicular there typically. What is it?
Would it be 10?
It is 10. You draw your radius, it's a 6, that's 8, 10. You see that? You see it? All right, we'll do one more. What if I have, that's a loopy circle. I'll put the little thing down here. And let's say this length is 24, and that is 5. What's the length of the radius?
20.
It's a Pythagorean triplet. What is it?
What?
What's this length?
Oh,
Wait, is it 5, 12, 13?
Yes, so what's the radius? 13, right? It's a 5,
I
12,
didn't see it was 24.
13.
I was just thinking.
Do y'all see that? Okay, yes?
So why didn't you put the radius on the same side as the?
It doesn't matter. It doesn't matter. Okay, could you also calculate the area? Sure you could.
Oh, yeah.
Sure you could. Okay, there's something else that is true. When chords intersect, this is what's not in your textbook. When chords intersect, it doesn't matter where they intersect. It doesn't matter. So you see I have, this is chord 1, this is chord 2. We'll label this segment A, that segment B. We'll label this segment D, we won't use C, D and E. The product of these segments of the chords are always equal, such that the product of the segments of chord 1 will equal the product of the segments of chord 2. That is always, always, always the case. All right, look at your handout. Look at number 16. Number 16 on your handout. I'm gonna draw it on the board. We have 14, we have X, we have 7, we have 12. We're gonna need your calculators. The products of these chord segments must be equal. So 14 times X must equal 7 times 12. What's 7 times 12?
84.
So 84 equals 14X. How do I solve for X? Yep.
84.
You divide 84 by 14.
And what is that?
6.
X equals 6. You can solve for the length of a segment. All right, everyone do 19, 22, and 24. 19, 22, and 24. Work this one. 19, 22, and 24. Sorry. Trying to help the people that are.
Which numbers did you say?
19, 23, and 24.
It's 23 or 22.
I have to turn it around. 22 and 24.
Okay.
19, 22, and 24. 19, 22, 24. Do y'all have it?
I feel like I'm doing this wrong.
The pieces equals 12 times X. So 15 times 8 equals 12 times X. Yes, ma'am.
So I'm not sure if I'm if I'm multiplying, I'm not sure which number X should be multiplied by.
Okay, number 19, what do you think?
I did 12X.
Equals,
120.
is that 15 times 8? That is correct. And then you're going to divide both sides by
12.
12.
So I got X equals 10.
X equals 10. Does everybody agree for number 19? X equals 10.
Yes.
All right, Alexis, what'd you get for 22?
I got X equals 12.
X equals 12. Is that correct? Did anyone not get 12? Everyone got it? Elliot, what'd you get for 24?
I got 14.
Did everyone get 14 for 24? Okay, excellent.